Welcome back to Mr. Hassan's Maths channel. I'm now going to be going through a question which is actually not from one of the normal papers that I do. I normally go through the International A-Level Edexcel papers, but I'm going to go through a GCE paper, which is a UK A-Level paper. This is the paper 1 for Pure Mathematics 8MA001 from June 2020. I'm going to go through question number 14, which is all about proof. And the reason I'm going through this question is because proof is a topic which is new to the International A-Level and in fact even to the UK A-Level syllabus. And so there's not many questions pre-2019 in this particular topic. So that's why I'm trying to get some extra questions. So I'm taking from the UK syllabus papers in order to increase the number of questions that students have exposure to in this particular topic. And if you do find questions which relate to what we're doing in International A-Level maths, then you should just request it. If I see the question is relevant and I see the question will help understanding of the students, I would answer it. So this is actually related to P2, okay, proofs, P2 proofs. So this is like the AS P2 from the International A-Level. It's related to that. And the first question, 14 part 1, it says a student states that if x squared is greater than 9, then x must be greater than 3. Determine whether or not this statement is true, giving a reason for your answer. Okay, so if x squared is greater than 9, so they're saying if x squared is greater than 9, and it says then, this is the statement, then x must be greater than 3. Okay, this is saying it must be true. Okay, now when you're dealing with square numbers, what you can think about is, for example, here it doesn't mention x having to be a positive integer or an integer or anything, so it could be any number including negative numbers. So we can straight away see that we can choose a number that's negative, which is when you square it, you get an answer which is greater than 9. For example, if I choose x equals negative 4, right, x equals negative 4, you can say minus 4 squared is going to give you 16. So we can say minus 4 squared is greater than 9. That's true. Okay, but minus 4 is not greater than 3. Okay, in fact, minus 4 is less than 3. Okay, so the statement is false. Okay, so we can say that a number like negative 4, okay, which is less than 3, but when squared is greater than 9, therefore the statement is false. The statement must be false. The statement is false because it's saying it must be greater than 3. If x squared is greater than 9, then x must be greater than 3. That's false, because minus 4 squared is greater than 9, but minus 4 is not greater than 3. Okay, so it would even work with, for example, if x is minus 3. Okay, although no, it won't, because minus 3 squared is equal to 9, not greater than 9. So no. So you start with anything that's less than minus 3. Okay, you will find that when you square it, you get something that's greater than 9. Okay, but when you, of course, itself is less than 3. All right, so that works fine. So any negative number whose magnitude is greater than 3. Okay, so any negative number like minus 4, minus 5, minus 3.5, whatever it is, will show this statement to be false. So this is like proof by counter example. You found an example of one thing that proves a statement to be false. Okay, so this is like that type of question. It's only worth 1 mark. Not much explanation needed for that. Now question part 2, 14 part 2, it says prove that for all positive integers n cubed plus 3n squared plus 2n is divisible by 6. Now, divisibility by 6, okay? Now, what we should remember from our, early years, understanding about like facts of divisibility and stuff, we know that, for example, if a number, is divisible by 2 and divisible by 3 as well, it is divisible by 6. So you can say any number. So I'm just going to state the premise, or what we're going to basically be concentrating on to try and prove this. Any number which is both a multiple of 2 and 3, both a multiple of 2 and 3 as well. Multiple of 2 and 3, not all 3 and 3, is a multiple of 6. Okay, so if we can prove that this expression, can be shown to be multiples of 2 and 3, then it will also be a multiple of 6. Okay, so now if we take this expression n cubed plus 3n squared plus 2n. Now, if I want to prove this, that's a multiple of 2 and 3 as well, for this expression, well, one way to do it is to think of ways of expressing all possible numbers as multiples of 2, and finding that when you put those values in here, you should get out things which will be in the form of multiples of 2, and you can show whether it's a multiple of 2 or not for every possible value of the number. Okay, so for example, I could choose when n equals 2k and when n equals 2k plus 1, where k is an element of the positive integers, because we're talking about positive integers here, right? So if I substitute 2k into here, and then I substitute 2k plus 1 into here, I should be able to express whatever I get from both of those as 2 times something, as 2 times an integer. So therefore it will be multiples of 2 for all these possible cases. That shows all numbers that exist. When k is 1, then this is going to be for example, when k is you can say when k is 0, let's say k is an element of all integers, no problem. When k is 0, then you can have when k is 0, then this will be 0. When k is 1, that will be 1. When k is 0, that will be 0, that will be 1. When k is 2, that will be 2, that will be 3. When k is 3, that will be when k is 2, that will be 4, that will be 5. When k is 3, that will be 6, that will be 7, so on. So it will include all the numbers that exist, every single number. And if you can show that you substitute these into that expression, you end up with something which is 2 times an integer. You've shown that this is always an multiple of 2. And for multiples of 3, we can try n equals 3k, and n equals 3k plus 1, and n equals 3k minus 1. And that will give you, that's all the multiples of 3. That's all the numbers which are 1 more than multiple of 3. And that's all the numbers which are 1 less than a multiple of 3. That includes every single number that exists. Okay, if k is an element of integers, when k is 0, for example, to be 0, that will be 1, that will be minus 1. When k is 1, that will be 3, that will be 4, that will be 2. Okay, when k is, for example, 3. So every number that exists will be able to be generated when you put 3k plus 1, and 3k minus 1 for all different integers of k, or values of k. You will end up with all the numbers that exist. And when you substitute these into that expression, you should be able to show that the expression gives you 3 times something in every case. So they're all multiples of 3. So then you prove it for all multiples of 2 and all multiples of 3, and you have then proved that this is always divisible by 6, because for all possible values of any integer, this will always be something which is a multiple of 2 as well as a multiple of 3. Now that's very long-winded, especially when you've got the expression like this. It's a very long-winded way of dealing with it, only for 3 marks. So to make life a bit easier, let's try to simplify this expression by factorizing. You can see there's a common factor of n. So you have n and n squared plus 3n plus 2. And this can also be factorized further. If we factorize this further, you have 2 numbers multiplied to give you 2 and add to give you 3. Well, that's n plus 2 and n plus 1. Now, if I rewrite this, I can see that this is n times n plus 1 times n plus 2. Now, we could go about doing this with these expressions, and we can prove by putting n equals 2k in here, n equals 2k plus 1 in here, you'll end up with something which is a multiple of 2 in both cases. And it's a lot easier than showing it in this. A lot easier because the way it's set up here as a product. And the same with 3k plus 1, 3k minus 1. Not too many steps. We can show that this is always going to also be a multiple of 3 when we choose 3k plus 1, 3k minus 1, thereby proving it's a multiple of 2 and a multiple of 3 as well. Therefore, it's a multiple of 6, because any number that's a multiple of 2 as well as a multiple of 3 will always be a multiple of 6 as well. Okay, because 2 times 3 is 6. But that again is a bit long-winded. If you can, I'm sure you can just state here that as we have, 3 consecutive integers. All right, we have 3 consecutive integers. So you have to give some sort of some justification. We can give this in words if we want to, but I'm going to also share how to algebraically as well, because that's an important skill that we should know how to, carry out in certain cases. So 3 consecutive integers will always contain a multiple of 2 and 3. All of them. Okay, because if you have, for example, e.g., let's just look at some example. 1, 2, 3. You have, for example, 3, 4, 5. You have, let's choose a random one, 47, 48, 49. Okay, all of them have a number which is a multiple of 2, okay, and a multiple of 3. Here you got 3 and 4. Here you got 47. 48. That's a multiple of 2 and 3 as well. Both of them. That's 2 times. That's 2 goes into 48. So does 3 as well, right? So every case you see, if you try different cases, you'll see that they'll all contain a multiple of 2 and 3, because multiples of 2 are separated by 2's. Okay, you have a number, then every alternate number is going to be multiple of 2, and multiple of 3's are separated by 3 numbers. Okay, so either a number is a multiple of 3, okay, the first number is a multiple of 3, then the next 2 numbers won't be, or the number in the middle is a multiple of 3, okay, and the other 2 won't be, or the last number is a multiple of 3, and the other 2 won't be. So one of them, if there's 3 consecutive numbers, must be a multiple of 3 somehow. Okay, and of course 3 numbers, we write them together, one of those numbers is going to be a multiple of 2 as well. So 3 consecutive integers multiplied together you'll be multiplying a multiple of 2 and a multiple of 3 together, so you'll end up with a multiple of 6. Okay, so 3 consecutive integers will always contain a multiple of 2 and 3. So therefore, okay, you can say the product of 3 consecutive integers will always be a multiple of 6. Will always be a multiple of 6. Therefore, we can say that n cubed plus 3n squared plus 2n, n cubed plus 3n squared plus 2n is a multiple of 6, is divisible by 6, all multiples of 6 are divisible by 6, is divisible by 6 for all positive integers n. Okay, so that's a proof, and that's fine. Okay, so that statement then, and you should write down, and we've proved it by this statement here. Okay, however, if you want to go through the algebraic proof, like, the whole thing from the beginning, only 3 marks, but I'm just going to show you how to do that so that you'll be sure. So for example, let's consider if n is even, then we can say let k be an element of the integers. So therefore we can say n can be 2k, or that's n equals 2k. And if n is odd, then n is going to be 2k plus 1. So if we can choose all the even numbers and all the odd numbers and show that in this expression you end up with an odd even number, we've shown that for every value of n, that this is every possible value of n, even and odd numbers, this is divisible by 2. So let's see, we're going to have, let's take it in this form. We have 2k times 2k plus 1 times 2k plus 2. That's n, n, and n. That gives you, of course, 2 times k times 2k plus 1 times 2k plus 2. That's 2 times an integer. Therefore, that's even. Okay, and if n is odd, okay, let's take it for 2k plus 1. We have n, which is 2k plus 1, times n plus 1, which is 2k plus 2, times n plus 2, which is 2k plus 3. Remember, it's n plus 1, n plus 2. So that's 2k plus 1, 2k plus 1 plus 1, 2k plus 1 plus 2. So we can see this here. We can rewrite this as 2 times k plus 1. This is now this. And then that's times 2k plus 1 and 2k plus 3. So we have here 2 times an integer. Okay, because this is an integer. Therefore, this is even. So we can show that for every number, every even number and every odd number, when you put that into this expression, you end up with an even number. Okay, so therefore we can state from this that n cubed plus 3n squared plus 2n is even for all values of n. For all values of n, therefore it's a multiple of 2. It's a multiple of 2 for all n values. All n values. Okay, we can say for positive, because they're asking us about positives, we're going to mention positive. All right, so we proved that now for all values of n. Okay, we proved that whatever value of n you put into here, you're always going to get an even number. Now let's prove it now when n equals 3k and n equals 3k plus 1 and n equals 3k minus 1. That will basically include every number that exists. Every number is either a multiple of 3 or one more than a multiple of 3 or one less than a multiple of 3. That includes every number that exists. So let's put n equals 3k into here and see what we get. This will help us to determine if it's a multiple of 3. So remember, we have n times n plus 1 times n plus 2. So when we put 3k, this becomes very simple. 3k times 3k plus 1 times 3k plus 2. We can see that this is 3 times an integer. Okay, very clearly. That's 3 times an integer. So it's 3 times an integer. Therefore, it is a multiple of 3. Okay, so we know this is a multiple of 3. Okay, for when n equals 3k. And when we put n equals 3k plus 1, we have 3k plus 1 times n plus 1, 3k plus 2 times n plus 2. That gives you 3k plus 3. So we can see this last one here. This one is like saying 3 times k plus 1. This becomes this. And then you're going to have 3k plus 1 and 3k plus 2. So this is 3 times k plus 1 times 3k plus 1 times 3k plus 2. I don't have to expand the whole thing here. I can show that this is 3 times an integer. Therefore, this is also a multiple of 3. So we've shown that this is a multiple of 3. Now we've got one case to consider, one less than a multiple of 3. So when n equals 3k minus 1, then we're going to have n, which is 3k minus 1, and n plus 1, which is 3k minus 1 plus 1, which is 3k. And that's going to help us. And n plus 2, that's 3k minus 1 plus 2, that's 3k plus 1. That gives you 3. If you take this 3 times k times 3k minus 1 times 3k plus 1. So that's 3 times an integer. Therefore, 3 times, or you can say, therefore, it's a multiple of 3. So therefore, we've proved that n squared plus 3n, n cubed, plus 3n squared plus 2n is a multiple of 3 for all n values. Okay, so I'm just going to just write down here, and instead of going to the next page, so we can say therefore, as n cubed plus 3n squared plus 2n is a multiple of both 2 and 3 for all n, therefore it is divisible by 6. Please excuse my bad handwriting here. Okay, but that actually, this last part here, I don't think it's quite necessary to go through. I just showed you how to show this algebraically as well, just because sometimes you might need to do that for certain types of question. But if you mention this statement here, that should be enough. If you mention this statement here, for these 3 marks, that should be enough. That 3 consecutive integers will always contain a multiple of 2 and 3. Okay, and that means the product of 3 consecutive integers will always be a multiple of 6. And if you want to show a few examples of that, like I did, like just choose 3 random consecutive numbers like 15, 16, 17. You can see multiple of 3, multiple of 2. 28, 29, 30. Multiple of 2, multiple of 3, and so on. You'll always find 2 numbers, sometimes the same number as we did, like I think that was 47, 48, 49. This number is a multiple of 2 and 3 as well. So this whole, if you multiply these 3 things together, you'll end up with a multiple of 6. So every consecutive integer contains, every 3 consecutive integers contain a multiple of 2 and a multiple of 3. So when you multiply them together, you'll definitely get a multiple of 6. Okay, so therefore, you can mention that, therefore, this is divisible by 6 for all positive integers. That would be enough for you to get the marks of this question, but this is just some sort of algebraic proof of the fact that this expression is divisible by 2 for every possible number that exists, and also divisible by 3 for every possible number that exists. Therefore, that means it's divisible by 6 as well. Okay, so as I said, excuse my bad handwriting here. Anyway, so those of you who want to see other questions from this particular paper, if I am asked to answer them from this question paper and I decide to do so, I will collect them together in the playlist that will appear in this section over here. When you click on that link there, over here you will find all the questions I've answered about proof from P2, including this deduction. This is like proof by deduction as well as exhaustion, and the other proof we did was proof by counterexample from question part 1. Other questions that you might want to, subscribe to my channel by clicking on this link, and the video that will appear in this region will tell you or show you how you can use my channel to find what you might want to watch more efficiently. Thank you for watching, and see you soon.